Oxidative cleavage is also known as ozonolysis. So ozonolysis. And we've seen this suffix lysis before. You would have seen it in general chemistry 1 when you talked about electrolytes. Electrolytes are things that break apart because of their electrical charge. They break apart in water. So ions that break apart in water because of their electrical charge. We saw it earlier in hydrolysis when you use water to break things apart. And in this reaction, in this oxidative cleavage, this ozonolysis, we're going to use a molecule called ozone to break pi bonds, to break alkenes apart, double bonds between carbons. Now, ozone is an interesting molecule. The air that we breathe, around 79% of the air we breathe, is actually nitrogen. It's molecular nitrogen, which is really, really stable. Maybe 19% of it is oxygen. Dioxygen is what it's called because you have 2 oxygen atoms there. That has an interesting reactivity of its own that we'll come back to in a future chapter. But a tiny, tiny amount of this dioxygen reacts with itself and becomes a separate molecule called ozone. And that looks like this. Now you'll notice that these lone pairs here are allylic to this pi bond. So ozone actually exists in this is not the true structure. The true structure is the average of this and the other resonance structure. Because those lone pairs are allylic, this exists in resonance, so you use those brackets to warn people. The true structure is not either of these structures in the brackets. It's only always the average of the 2 structures, and you draw this special resonance arrow with 1 line and 2 heads to tell people to take the average of these 2 structures. And whenever you have an allylic lone pair to draw the other resonance structure, the lone pair goes toward the pi bond, and the pi bond breaks and creates a new lone pair away from the pi bond that's forming. And so you'd have this. The structure there. So the true structure doesn't have single and double bonds. It has something in between. If you average, say, the single bond here and the double bond in the other resonance structure, you get something in between. And the charges are also something in between. So ozone is a resonance-stabilized trioxygen molecule. It's a light blue gas, and it has a sort of pungent odor. Some people think it smells a little bit like chlorine. And sort of if you go to a pool that has a lot of chlorine in it, you kind of know what this ozone would smell like. It ends up being really reactive, as we'll see. This reaction we're going to talk about, we have plenty of double bonds in our bodies. Both us as animals, plants have the same thing. And so ozone will react with that, and it's kind of caustic. So it will harm our bodies at high enough concentrations. The safe concentration is below 0.1 parts per million. Above that, you'll start to smell it. It'll start to react with your respiratory tract, which may burn or what have you. So at ground level, ozone is not that pleasant of a thing. You can sort of almost think of it as a pollutant. However, in the upper reaches of the atmosphere, it helps us a lot because it protects us from ultraviolet radiation from the sun. If you think about our solar system, 99.9% of all the mass in our solar system is in the sun. So if you take all the masses of Earth and the other planets, all of the over 200 moons that exist in our solar system, and you add them all up, with all the asteroids, both in the Kuiper Belt and the Oort cloud, if you add all of that up, it still adds up to only around 0.1% of the mass of the sun. And the sun is so hot that all the protons, neutrons, and electrons in it are too energetic to form atoms. They're called a plasma, which is where you have protons, neutrons, and electrons just in a hot, chaotic soup, whizzing past each other. And you can imagine all of that energy belches out and releases all sorts of high-energy particles. Those particles are ejected in every which direction, and that's called the solar wind. Now, in addition to the particles, you have a whole bunch of really energetic waves of electricity, which we would think of as different forms of light electromagnetic radiation, and one of those are the UV radiation that this ozone protects us from. That solar wind, by the way, if it knocks into the atmosphere particles just the right way, it'll make the molecules in our atmosphere light up, and that's responsible for the auroras, like the aurora borealis. In any event, this ozone is important because it protects us from ultraviolet radiation, and in places in the world where the ozone is depleted in the upper atmospheres, the ultraviolet radiation comes through and there's a much higher incidence of skin cancer. People have to be much more careful about wearing sunscreens before they go out. That's the case, for example, in Australia. Okay. This ozone is a sort of light blue gas. As you cool it down, it turns into a dark blue liquid, and if you make it even cooler, it turns into a sort of violet-black solid. But we would deal with it as a gas. It is a little explosive. That's the other problem here, and the intermediate that you form in this reaction is also really explosive. So let's see how this could react with an alkene. So if you take ozone, the oxygen with the full negative charge is reactive, and these electrons in this pi bond, those want to stabilize this positive charge, so you sort of have a push and a pull all at the same time that creates a sort of cyclic reaction. You have a push where this wants to attack something, and you have a pull where these electrons want to stabilize that positive charge. To make all those things happen, the pi electrons in the alkene attack this oxygen. So as these move, they make room for the incoming electrons, and they allow the outgoing electrons to stabilize the positive charge. And that creates an intermediate called an ozonide. So an ozonide, and what you'd have there, what that would look like, would be something like this. Okay, and so that is your ozonide. Now each of those oxygens has a zero charge now. And this sort of crumbles apart. You have these bonds between oxygens, and we've seen this before in the case of peroxides and peroxyacids. In the case of peroxyacids, we talked about it when we talked about anti-dihydroxylation. Bonds between oxygens are very unstable, and so those electrons are looking for somewhere to go. And the first thing that happens is one of them sort of crumbles, and it can feel the positive charge on this carbon. Right? These carbons have a sort of positive charge because they're bonded to an oxygen, so that's a polar bond. The oxygen is slightly negative, the carbon is slightly positive. So these electrons are unstable where they are, they feel a positive charge over here, and so they rush towards it. Now this carbon already has 4 bonds. If it's going to form a new bond, one of them has to break, and the most electronegative place nearby is this oxygen here, so that moves over. So you get this sort of rearrangement, and you'll see that now, if you look at this bottom part, if you think about that, this is now a double bond to that oxygen. And all you have is the one hydrogen here that was here before, that hydrogen. And on the other side, if you think about this, you end up with those 2 carbons. You're now double bonded to the oxygen, single bonded to the other oxygen from ozone. Oops. Okay. So that is one of the steps in here. And actually, I drew this. I should have drawn this from these lone pairs here. And so here, oops, this goes onto there. So here you end up with this negative charge here, And you end up with these double bond, the bond between the carbons is broken, crucially. So this bond breaks, notice. It becomes first a sigma bond, and now it's just broken altogether. And what it was, where it was, is replaced by double bonds to oxygens. So that's the feature that we're going to use in the synthesis problems. We're going to sort of break this bond open and replace it with double bonds to an oxygens. Now, the rest of the mechanism is a little long and convoluted, and maybe not the most important thing for our purposes, but I do want to mention the second step for this, and that's adding DMS. DMS is dimethyl sulfide. So that looks like this. You have sulfur, it's the S, and then two methyl groups on either side, so dimethyl. And this is not what happens, but the general idea of what happens is that this oxygen gets transferred to the sulfur. So it doesn't just magically float there, it has a long, long procedure. This actually ends up forming another ozonide. After this one breaks, these come together to form another one, and then there are a bunch of steps to break that apart. But the general idea is the oxygen gets transferred to the sulfur in DMS. And it actually ends up forming a double bond to it, and it becomes dimethyl sulfoxide. DMSO was a polar aprotic solvent that we saw that favored SN2 reactions when we were talking about substitution. So it's a sort of a callback there. The DMS is related to that DMSO. Now notice what these two features are that we made. These actually introduce a new functional group. This bottom one is called an aldehyde. An aldehyde is when you have a carbon double bonded to an oxygen with a hydrogen on one side. The smallest aldehyde is if you have a hydrogen on both sides, and that's an aldehyde you're probably familiar with. That's formaldehyde. This top one is called a ketone. A ketone is where you have a carbon double bonded to an oxygen with a carbon on both sides. So these are groups of atoms that always behave the same way, so they're called functional groups. Groups of atoms that always function the same way, aldehydes and ketones. So when you do ozonolysis on an alkene, you form either aldehydes or ketones, or you could form both. And you'd be familiar with ketones. The suffix ONE is often in ketones. So for example, testosterone ends in ONE because it has a ketone in it. Okay, so overall here, the general idea is we treat an alkene with ozone, O3, that breaks that pi bond and turns it into double bonds to oxygens. And then DMS comes in and steals the third oxygen to become DMSO, dimethyl sulfoxide. We end up creating aldehydes and ketones. Okay, so hopefully that will help a little bit with just some context and background for ozonolysis, or oxidative cleavage of these alkenes. So I just want to add one small clarification for the breaking apart of this ozonide intermediate. These lone pairs here are attracted to the slightly positive charge. Lone pairs on this oxygen are attracted to the slightly positive charge, so that goes to form a pi bond there. At the same time, that kicks this off to make the pi bond there, and that in order for that oxygen to form a new bond, it has to break one, and it breaks this oxygen bond here. So you end up forming a double bond to oxygen, and here, double bond to oxygen with an oxygen there. And this oxygen here eventually gets transferred to dimethyl sulfide to become DMSO. So you end up with those same products that we talked about before.